NumPy stands for Numerical Python. It is the most widely used library in Python for numerical computing. Unlike Python lists, NumPy arrays are stored more efficiently in memory and allow us to perform fast mathematical operations on entire datasets at once. NumPy is the foundation for almost all data science and machine learning libraries, like Pandas, scikit-learn, and TensorFlow. In marketing analytics, we use NumPy to handle customer data, run calculations quickly, and prepare data for statistical models. So before we move to advanced tools, it's essential to understand NumPy basics. A NumPy array called ND-array is similar to a Python list, but it is much more efficient for numerical data. Arrays can be one-dimensional, like a simple list of numbers, or multidimensional, like a table or matrix. This creates a one-dimensional NumPy array with the values 1 through 5. Notice that the output is written without commas, showing it is an array, not a list. This is the same sequence stored as a Python list. Lists are flexible but slower for large computations compared to arrays. This is a two-dimensional array, often called a matrix. It has 2 rows and 3 columns. The attribute shape confirms its dimensions, 2 by 3. NumPy provides convenient functions to initialize arrays, zeros, ones, ranges, evenly spaced values, or random numbers. Zeros creates a 2 by 2 array filled with zeros. Ones creates a 3 by 3 array filled with ones. Random creates a 3 by 2 array filled with numbers between 0 and 1. Each time you run it, you'll get different random values. One key advantage of NumPy arrays is element-wise operations. That means addition, subtraction, multiplication, and division happen across all elements without loops. Here, RR1 plus RR2 produces element-wise addition, 1 plus 4, 2 plus 5, 3 plus 6, giving 5, 7, 9. Subtraction, multiplication, and division all follow the same rule applied across each element. Arrays can also be scaled by a single number. Here, R1 times 3 gives 3, 6, 9. NumPy functions like square root and exponential apply the operation to every element. This makes data transformation much faster and simpler. Like Python lists, arrays support indexing and slicing, but with multiple dimensions, we use row and column positions. Index 0. 0 selects the first row and first column, 1. Index 2. 1 selects the third row, second column, 8. Also, index 1, 2 gives 6. Slicing row 0 to 1 and column 1 to 2 gives a 2 by 2 subarray 2, 3 and 5, 6. We can also select entire rows or columns using a colon. To select the entire row of column, we can ask for row index 1, which is the second row, and the colon in the column position means take all columns. Also in the next line, the colon in the row position means take all rows, and the 2 in the column position means only column index 2, which is the third column. Finally, Boolean indexing filters values that satisfy a condition. Here we get all values greater than 5. NumPy makes it easy to summarize data, totals, means, maximums, minimums, all with single functions. Sum without axis adds all elements together, giving 45. With axis 1, it sums rows, 6, 15, 24. With axis 0, it sums columns, 12. 15, 18. Mean calculates the average. Max and min give the largest and smallest numbers in the array. These functions are extremely helpful for quick analysis of datasets. Let's practice NumPy basics, creating arrays, performing operations, slicing, and aggregating. Pause here and complete. np.arrange generates a sequence of numbers. Here it creates an array from 1 to 10 inclusive. This makes a 3 by 3 array with values 1 to 9 arranged row by row. Addition gives 5, 7, 9, subtraction gives -3, -3, -3, and multiplication gives 4, 10, 18. These are element-wise operations. Multiplying an array by 5 scales each element, resulting in 5, 10, 15. Slicing rows 0 to 1 and columns 1 to 2 gives a 2 by 2 subarray, 2, 3, and 5, 6. Using colon syntax, we can select the entire first row or the entire last column. That gives 1, 2, 3, and 3, 6, 9. This one-dimensional array has mean 30, maximum 50, and minimum 10. NumPy makes summary statistics easy. Reshaping changes the structure of arrays without changing the data. This is essential when preparing data for models. A one-dimensional array of 6 elements is reshaped into a 2 by 3 matrix. Using order F fills the array column by column instead of row by row. Flatten collapses a multi-dimensional array back into a one-dimensional sequence. The transpose swaps rows and columns. Here, a 2 by 3 matrix becomes 3 by 2. Vertical stacking puts one array on top of another, so each input becomes a new row. Use it when you want to add records. Horizontal stacking joins arrays side by side to extend columns, so use it when you want to add features. Before stacking, quickly check shape to make sure column counts match for vertical stacking or row counts match for horizontal stacking. Splitting breaks a single array into multiple pieces. Split expects even parts, while array split can handle uneven sizes. Quick rule: ask yourself, do I want more rows or more columns? Then pick VStack or HStack, and if sizes don't divide evenly, use array split. Broadcasting allows arithmetic between arrays of different shapes by stretching dimensions automatically. A scalar like 5 is broadcast to each element, giving 6.78. Here, the one-dimensional array 10, 20, 30 is broadcast across 2 rows, producing a 2 by 3 result. We start with a 2 by 3 matrix. First row, 1, 2, 3. Second row, 4, 5, 6. The scale factors array contains 2 elements, 2 and 3, 1 per row. To apply them row-wise, we convert the one-dimensional scale factors into a column vector by using NumAxis, so its shape becomes 2 by 1. Multiplying the 2 by 3 matrix by that 2 by 1 column broadcasts the column across each row. The output is the first row doubled, 2, 4, 6, and the second row tripled, 12, 15, 18. A quick tip: you can use scale factors, none instead of NumAxis. Both make the column shape you need. Here the matrix is 2 by 3 again, and the vector is length 3. NumPy broadcasts the length 3 vector across each row as if we had copied it to match the number of rows. So we add 1, 0, 1 to each row. The first row becomes 2, 2, 4, and the second row becomes 5, 5, 7. The key rule is shape compatibility. A 2 by 3 matrix can add A3 vector because the trailing dimensions match. If shapes don't align, NumPy will raise a shape error. Advanced indexing uses arrays of integers or booleans to select or modify elements. This selects specific positions 0, 2, and 4, giving 10, 30, 50. A boolean condition produces false, 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 true, true, true. Using it as an index filters only values greater than 30, 40, 50, 60. Boolean indexing can also modify arrays. Here, all values greater than 30 are replaced with 0. This prints the 2D array but keeps only the first and third columns. The expression ARR2D uses a Boolean mask on the column axis. True means keep that column, so the output is 1, 3, and 4, 6, and 7, 9. Here's a tip. The mask length must equal the number of columns, otherwise NumPy raises an error. NumPy includes linear algebra functions, dot products, matrix multiplication, determinants, and solving equations. The dot product multiplies and sums element-wise. 1 times 4 plus 2 times 5 plus 3 times 6 equals 32. This performs standard matrix multiplication. The result is a 2 by 2 matrix 19, 22, and 43, 50. The determinant of this 2 by 2 matrix is -2. The inverse matrix is -2, 1, and 1.5, -0.5. Here we solve the equation x, b. The solution vector is 2, 3. NumPy's linear algebra module handles these calculations efficiently. Let's practice what we studied so far. Please pause now and complete the code. Reshape changes layout only. The number of elements must match. Flatten collapses to 1 dimension. Column first reshaping uses order equals F. Make a 1 to 12 array and reshape to 3 by 4. Same values, new shape. Flatten back to 1 dimension, then reshape to 2 by 6. This works because the total count is still 12. Next, broadcasting lines up trailing dimensions. Vectors stretch across rows and scalars apply to every element. Add a length 3 vector to a 2 by 3 matrix. NumPy broadcasts the vector across both rows and adds element-wise. Add 5 to a length 3 array. The scalar broadcasts to every entry. Integer indices pick exact positions. Boolean masks filter by condition, and the same mask can be used to assign. Filter values greater than 10. Only entries where the condition is true are returned. Use matching row and column index lists on the 3 by 3 array to grab specific elements directly. Last, dot multiplies and sums. Matmul is row by column. A zero determinant means singular. Inverse exists only if non-singular. Solve finds x in ax equals b. Compute the dot product of two vectors, multiply matching entries, and sum. Matrix multiply the two 2 by 2 matrices to get the result matrix. Compute determinant and, when possible, the inverse. Solve ax equals b to get the solution vector. NumPy arrays power fast, loop-free math. Today, we created and reshaped arrays, indexed rows and columns, filtered with Boolean masks, summarized by axis, and used broadcasting so vectors and scalars align automatically. Remember 2 rules. Always check shapes and reshape changes layout, not values. Thank you and see you next time.